So far we were talking about undirected graphs, but now let's talk about directed graphs because directed graphs come up very often in algorithms. Okay, so a directed graph is also a two tuple, a set of vertices and a set of edges. And the edge now is a ordered pair of vertices. So whereas before we had curly brackets around two vertices to represent a set, i.e. an unordered list, now we have parentheses to represent a ordered list. Okay? This directed graphs are arguably more relevant to most situations than undirected graphs, because road networks, like many physical objects, one way one way things one way things, and web links are also often one way. Um, Making files for compiling programs, the if you guys use Anaconda, like the dependency of different libraries to each other, all one way. Many most problems you're going to deal with in an applied manner are one way, and thus you need directed graphs. So, similar to undirected graphs, you could represent directed graphs in two ways. You could have a adjacency matrix or adjacency list. So the default representation, like before, is adjacency list. But the one difference is that whereas before in the adjacency matrix for undirected graphs, you had a mirror image. For directed graphs, the adjacency list isn't mirrored along the diagonal. It's different, right? Because you could have an edge that goes from U to V, but you don't necessarily have to have the edge that goes from V to U. Similarly, for adjacency lists, now each edge is truly listed only once in the adjacency list. And there are two types of adjacency lists. There are the adjacency lists which store the edges that are going out of the node, so noted as out U, or that is the default that we use. We simply each of the basic each of the list indices is U. So the lists themselves represent the edges that are leaving U. However, there are many algorithms that would benefit from quick lookup of all the edges that are coming into U. And so transforming one to the other is not difficult, it's almost trivial. But the issue is that we don't want to say that algorithms that use in U adjacency lists are worse than algorithms that use out adjacency lists. This shouldn't be like a one format is better than the other type deal, right? So you could specify either in your when you're writing your algorithm. You could specify either. You don't have to account for the penalty of transforming a out U adjacency list to an in U adjacency list. Okay, that's a major point I want to make. So concrete representation is the adjacency list, namely out U, and the array of edges for easy to look up for easy search through all the edges. And similarly, the definitions for directed graphs are pretty similar as for the undirected case. A directed path is a sequence of distinct vertices vi through vk, such that every two adjacent vertices have an edge, or an edge exists in the graph for every two adjacent vertices, and the path is of length k minus 1. And again, a single node U is a path of length 0. Cycle, similar thing, except that there must be an edge from vk, the last node, to v1. And we say a vertex U can reach V if there is a path from U to V. Okay? And then we define a new function called reach U. which is the set of all vertices reachable from you. Okay, so this function itself outputs a set of vertices, not just one vertex. Okay, and so this reach becomes a very important concept in a lot of different graph algorithms that deal with directed graphs. So over here, we want to note that that reach is not symmetric, namely reach is asymmetric because B, for instance, can reach D, B, E, G, no, B, E, what am I doing? Oh, D can reach B. Sorry, D, I read that wrong. D can reach B, but B cannot reach D. Okay, so reach is asymmetric, but there are cases where all the components, where you have a set of components that can all reach each other. So for instance, this set of components, B, E, and F, could all reach each other, right? These are all form cycles. So that's a pretty important concept also. In undirected graphs, as long as there is a path between two vertices, then they're strongly connected. You could go from one to the other and back and forth. But in directed graphs, just because there's a path from D to B does not mean that there's a path from B to D. So the fundamental questions of, is there a concept of connected components in directed graphs, and how do we understand connectivity in directed graphs? And that's what we will discuss next.